Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. I'd like to start off our event today by thanking Databricks for sponsoring today's event. Databricks is an integral supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Tableau, SAS, IBM, Qlik, and SAP, to name just a few. Now, our past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Now, today's webinar is entitled Matei Zaharia's Predictions for 2018, Big Data and AI Highlights. And of course, that'll be presented by Databricks. Before we begin, I'd like to briefly review the format for today's webinar. Today's event will be an hour long. We have one presenter who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Matei Zaharia with Databricks. Matei is co-founder and chief technology officer at Databricks. He started the Spark project at UC Berkeley and serves as its vice president at the Apache Foundation. He's also an assistant professor of computer science at Stanford. Matei contributed to several other widely used open source projects, including Apache Mesos and Tachyon, which he co-started, Apache Hadoop, and key components of Spark such as mlib, Spark Streaming, and Spark SQL. He was awarded the ACM Doctoral Dissertation Award in 2014 for his research in large-scale computer systems and Best Paper Awards at NSDI and SIGCOMM. Matei received his PhD in computer science from UC Berkeley and holds his bachelor's in mathematics from the University of Waterloo. So Matei, thanks for being with us today. We're looking forward to your presentation. Now, over the past few years, AI and big data have powered numerous technologies that have changed the way we live, from autonomous cars to conversational systems to personalization. As a result, the excitement around these technologies has spiked. But how can we separate the hype from the reality? And which advances will make an impact in practice next? So in today's DSC webinar, Databricks co-founder and Stanford computer science professor Matei Zaharia, who also started the Apache Spark project, will share his perspective on which big data and AI trends will come to fruition in 2018. He'll discuss how centering organizations around high-quality data will be the main driver to AI, which applications are seeing broad success in practice, how new technologies, including deep learning, data marketplaces, and cloud computing will affect the computing landscape. And so in today's webinar, we'll discuss the current state of big data and AI, some new innovations taking place in research, key challenges that companies face in getting value from data and AI, and Matei's predictions for 2018 for how companies and the technology industry will overcome these challenges. So Matei, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
All right, thanks a lot, Bill. Thanks for having me on Data Science Central. So yeah, excited to be here. As Bill said, this webinar will be trends and predictions for 2018. So I'm going to talk about trends that we're seeing at Databricks, at our customers, and also in general in the research community around AI and big data. And even though it is a webinar more about broad trends, I'll try to put in some technical explanations of some of the things where needed to explain where these things are coming from. Before I begin, just a little bit about Databricks, where I work. We're a company founded in 2013 by the team that started the Apache Spark project at UC Berkeley. And we provide a cloud-based unified analytics platform for data teams. So what that means is a complete environment for building pipelines and products based on data. It includes sort of three key components. It includes the Databricks runtime, which is Apache Spark plus a number of optimizations that can make it an order of magnitude faster in the cloud and also reduce cost by a significant amount. It includes a collaborative workspace environment for working with notebooks and jobs as a team, and it includes features for enterprise security and compliance. And we work with over 1,000 customers across Amazon Web Services and Microsoft Azure. These are just some of our customers here. You can see that they sort of span the range all the way from financial services to healthcare, media and entertainment, technology, and so on. And all of these customers are working with large-scale data sets and also with AI applications. So let's just briefly talk about the state of big data and AI in the industry right now. It's very clear, it's been the case for many years that many organizations are collecting and making use of big data, and it's definitely valuable for everyone to work with that. And there's a lot of interest in AI as one of the applications. It is, for everyone we talk with, some form of AI or machine learning is usually the end goal, though, even doing basic things with the data course gets them very far, but this is kind of the goal. And there are a lot of early successes with it as well. At the same time, though, I think everyone who follows this field knows that there is a ton of hype around artificial intelligence in particular, and there are fewer successes in real businesses. So you see, many companies who show off the latest thing they can kind of do, cool demos, playing video games using AI, this kind of stuff, which is very impressive. But at the same time, when you try to apply it in practice, it's challenging, and many of the early results disappoint. So I want to talk a little bit about why we see that happening, and what are some of the trends that are happening in the industry to deal with that. And of course, this includes things that we're doing at Databricks and also that we're contributing to Apache Spark. So I'm going to talk about 5 different trends and predictions in this webinar. The first one is how data is and will continue to be the key competitive advantage. I think this is something that a lot of people don't fully grasp, and this is one of the main reasons why AI project may or may not be successful. And we see actually the whole industry is centering itself around this aspect. The second one is about vertical-specific use cases. So how do you get AI in the hands of more and more users in specific domains? I'll talk a bit about the people working with data and machine learning, which are data scientists. And then I'll talk about software that people are using as well, in particular the deep learning frameworks and also new architectures and systems for just managing data as a whole, where there's a lot of interesting stuff happening in both of these areas, largely due to sort of those first few trends that I'm going to mention. So let's dive into it and start with data as the key competitive advantage. So I think everyone who works in the field will tell you that data is what really powers AI. AI models can only learn from diverse and high-quality data. What I mean by that, by diverse, I mean it has to cover many of the cases that, or essentially all of the cases that will occur in practice in some form. And high quality means that the data has to be accurate. So, if you have, for example, labeled data with some labels of like, hey, say we got this message from a customer, what product was it about, or something like that. That label needs to be accurate for most algorithms to work. And building data that's diverse and high quality can be quite difficult. The other interesting thing here, which may not be super obvious, is that more sophisticated machine learning models actually require even more data than a simpler model. And that's because they have many parameters that you need to train. And basically, you need, in order to avoid statistical problems such as overfitting, you need more and more data points to actually train such a model. So, for example, deep learning is a very kind of popular sort of new technology recently. All of the deep learning models that you hear about that are setting, records for things like image recognition or translation or things like that have tens of millions of parameters. And for training, they work with millions of images, text documents, drives of a self-driving car, and so on. That's the only way you can train a large model. So the better, in some sense, or the more complex the model is, the more data you're going to need as well to get really good predictions from it. So if there's one kind of summary for, this trend, it's basically it's the data stupid. This is the new version of it's the economy stupid. Whenever, I work with anyone who's building an AI project and they have an issue, with something not working, often it's an issue about the input data or the way it's being transformed and so on. And then on the other hand, if you have really good data, it's much more straightforward to build a good model out of it. So let's look at this in a little bit more detail. Let's start by looking at web companies and their success with AI. So definitely today, the most successful AI projects are those that are based on the web, which happens to be the largest public data set we have of sort of human-generated data. So these are things like image recognition, translation, search, speech, and so on. If you want to just see lots of labeled images of different items, the web is excellent for that. You can easily download basically hundreds of millions of images that people have written something about and use that as input to an algorithm and have a really good product that, when you take a picture on your phone, it tells you there's a palm tree in it and there's like a beach ball and whatever else. So these common objects with lots of images are easy to find. Same thing if you do anything with text of kind of the general nature of text that appears on the web. You can easily predict the next word that people will type and stuff like that, and build really good text-based things. Now, from a kind of outsider perspective, just looking at the field, this might seem like a really great result and outcome because it means, we're working with this largest data set in the world and we've scaled AI to work on it. So if it works on the web on petabytes of data, it's got to work on everything else. But if you look at it from an AI perspective, it's actually the opposite case. In some sense, beyond the computational challenges of scaling things out, which are important, from a statistical and AI point of view, these are basically the easiest AI problems. You have so much data to use that it's actually pretty easy to predict, new outcomes and so on based on the data points that you have. So really, the most interesting thing in machine learning and statistics and AI is how do you predict from much less data where you don't have enough to cover your specific cases. So let me just show you a quick example to illustrate that. So let's imagine we have a company here that has a bunch of customers that's making loans to, and it's trying to predict how much of the loan they're going to repay in the first year based on their credit score. So first of all, here we have a company with very few data points on their past customers. They just got a few points here. And you can kind of see, there's kind of this trend where if their credit score is low, they don't repay as much in the first year maybe as if their credit score is high. But that's pretty much the only thing you can tell from this data. There's not much you can do beyond that. So, for example, if a new customer comes in and you look at their credit score and it's somewhere in the middle here on the x-axis at the bottom, what are you going to predict as the amount repaid? It's probably more than the ones on the left. It's probably less than the ones at the right, but you don't know a ton about it. You might maybe predict something in the middle. It's kind of the best you can do. And if you are trying to model this, you could have, you could decide between many different models for this. Is this like a linear model where it would be exactly in the middle? Is it some kind of like exponential, or is there a threshold where past that threshold people are likely to repay the whole loan? You can spend a lot of time kind of theorizing about that, but just from the data, it's pretty difficult to do anything else. Now, imagine another company in the same business who just happens to have more data points. And now you have data points covering every possible credit score. You have lots of them. And now you're trying to predict how much someone will repay. Well, in this case, it's super easy. You don't even need a very sophisticated model. If someone has a credit score here in the middle, whatever this value is, you just look at the range of values around that. You can actually see not just the average amount that people repaid, but even a range. You can say, 90% of people repaid stuff, between 5 and 20% of the load or something like that. And it's super easy to make predictions using even an algorithm as simple as nearest neighbors, which is you just take the closest data points to the one you're looking for, and you predict the average of those. So that's the difference that having a lot of data makes, and that's why the more data you have, the easier the problem is from a statistical perspective, and you can actually make better predictions. The other point I want to make here is that it's not just the quantity, but also the quality of the data that matters. In particular, the training data for AI needs to cover all the real-world cases in a good amount of detail in order to let the algorithms extrapolate. So if you look at the graph here, we have a company, again, that has lots of data, the blue points, but they're missing points about anything in this middle range. And the extra data isn't really going to help them make a prediction there. They're kind of in the same spot as our initial company, even though they have, 10 or 20 times more data points in total. So there are a lot of examples of this in the real world. If you look at everyone developing self-driving cars, for example, they're trying to collect, millions of hours of drive data where the car or where a person is driving in different weather conditions in different parts of the country, with different types of roads and intersections and so on. And the reason is if you don't have data covering some cases, it's quite difficult to predict how the AI model will do in that case in the future. So that's why these companies are investing so much in these fleets to collect this data. Really famous example is face recognition failing based on races. There were all these examples of products that don't recognize that there's someone's face there because they were trained, say, only on Caucasian faces and light skin tone, and then they just couldn't recognize a dark one. That's a perfect example of the training data not covering all the cases. And the other thing you'll notice here is that in any environment that's changing, you also need continuous retraining to put in the new data. So even if you think of like a phone assistant like Siri or something like that, the types of questions people ask will not be static. The types, all the businesses, all the things you can search for in Siri will be changing all the time. And so you need to keep the data up to date. So that's one aspect of the quality aspect is that training data needs to cover all the use cases. The second aspect, which is a little bit more subtle, is that there's also a risk of overfitting to a training environment. So if you have a large model, such as a deep learning model, you need to take particular care about what exactly are the features of the data you collected, and is it representative of the way you'll collect it in the real world after you do the training. So I'll show what I mean by that with an example. So there were a bunch of interesting studies in the past where people tried to predict someone's gender from a picture of their iris, just a picture of their eye. They look at it and they say, oh, that's a woman or that's a man. Seems pretty impressive because, when we look at other people, at least I can't tell a huge difference between how their eyes look. They look the same to me. And so these studies were applying deep learning to this problem. And as they applied bigger and bigger deep learning models with more layers and more features, they would go up in accuracy from, say, 60%, 70%, 80%. And that's a very high rate of finding things. Now, later, someone tried to look at all the models they produced and all the images, and they discovered that in the particular training set they were using, the pictures covered more than the iris, and a lot of the women were wearing mascara. So what actually happened is that the deep learning model, which looks at textures anywhere in the picture, observed and learned about the mascara around there. So it could now predict based on that. And that's definitely not what everyone had in mind when they did these studies. They really wanted to focus on the iris, but because you have a complex model that can take in all the data and can represent a feature that represents mascara, it was able to learn that. So that might seem like kind of a funny story, but when I talk to people, for example, researchers in medical AI and things like that, it becomes a serious concern. For example, one researcher I work with looked at basically diagnosing patients based on MRI images, and he told me that he worries that for his study he's got data from one hospital which has a bunch of sick patients with a disease, and then from another hospital where they're just people without that particular disease. And now he's worried that maybe the model that predicts whether someone has the disease is just learning about features of the MRI machine in the first hospital. Maybe the images it produces are slightly sharper or something like that. That's definitely not great. So this is a second example of a data problem you have to deal with. So how is this going to affect the broad industry, how people use AI, how they work with it? Well, I'll put in two sort of predictions. The first is that the most successful organizations with AI will be those with large amounts of diverse, high-quality data. And something that's kind of good news here for everyone is that it's likely to be many different organizations and companies in each domain. It's not going to be just, say, one web company who becomes an expert on everything. Instead, the company that has, say, the most information about car loans will become good at predicting stuff about car loans. The company that has the most information about radiology images will become good at that, and so on. So in some sense, that's kind of good if you're in a business that collects or has access to a specific type of data, or maybe to interesting combinations of data sets. So the key then to be successful is to collect and combine these diverse data sets and do it continuously to update over time, which is exactly the big data problem. And that's why it's no accident that all the companies doing this have invested a lot in big data. The second, I think, interesting prediction and trend we're seeing is that more organizations will sell access to data as a line of business. There are already quite a few organizations today that do this, especially, for example, in the financial space. All the stock exchanges, you can subscribe to a data stream and get information about all the trades and so on. But we think that there'll be new ways that this happens as well. So, for example, one thing we're seeing is that with cloud computing, it's possible to charge people by the query. Not just sell them a subscription where they get a dump of all the data every day, but charge in a pay-as-you-go fashion. And we think this trend will continue as well as organizations look at what they can do with the data they've acquired. So that's basically, if you take away one thing from this talk, is it's the data stupid. In most AI applications, the quality of the data is what determines the success, and also any problems in the data are what causes problems and requires debugging and so on. So that's, I think, the biggest trend that we'll see the industry organizing itself around. All right. Second thing I want to talk about is how AI will reach more users and about vertical specific use cases. So it's a natural question. There are some early companies that just have, they just build everything from scratch, and they have successes. But how can it reach 10 or 100 times more users? And the most likely vehicle that we see is vertical specific solutions, or basically software that solves specific problems in a business domain that arise across many organizations. And many of these also provide a framework for customization by each organization that uses them. And this particular type of system is greatly empowered by open source. So we've actually seen a lot of these in the Apache Spark community. As an example, I'll talk about health and life sciences, one of the industries that has, the most, both the largest and some of the most diverse types of data available. So there's been decades of work on bioinformatics on tools for basically computing with biological data. In the past, a lot of these tools were kind of small scale, designed to run on a single server. About 5 years ago, many of these tools started to use Apache Spark for scaling. And now today, you can find a lot of open source tools that operate at the larger scale. And there's basically some of the most popular tools in this space. So some examples, the Genome Analysis Toolkit, or GATK, is probably the single most common tool used for processing genomic data read from a sequencing machine. It's used in thousands of studies every year, and today it handles parallelism using Spark. HALE is a statistical analysis toolkit from the Broad Institute in Cambridge, which is also one of the largest scale tools for finding statistical correlations between genes and different attributes of a patient. ADAM is a storage format based on Apache Parquet, and there's this whole big data genomics stack of open source software based on basically the open source big data stack. We're seeing customers use these tools for a number of different use cases, all of which combine multiple types of data that they have. So genomics and precision medicine, or targeting basically the drugs for someone based on their DNA sequence, as well as other attributes of that one patient, improving patient care, and AI-assisted diagnosis, so telling a doctor about similar patients and similar cases based on features of each patient. And in all these use cases, data is really the driver, but of course the open source technologies are what allow many organizations to share, to share their results and their expertise and build good applications using it. So there are many different types of data that can go into these, anything from DNA sequencers and clinical data like medical records to information about drug screening and development. A lot of drug development today happens basically through robots that try out thousands of molecules and look at their impact on different things, social data, and sensor-device data from wearables. And what users are doing is taking all of these, combining them using a platform like Databricks, and then building these applications on top. And the most interesting applications usually combine several types of data. So that's kind of the way that we see organizations kind of expanding the use of AI, both internally and across organizations. And we see a lot of people basically building reusable notebooks or jobs or software libraries to do specific tasks. And then the next year, they're applying them, to 5 or 10 new problems. And health and life science is just one field. The same thing is happening in many other areas. So just in Apache Spark, for example, there are libraries that have come up in the past 2 or 3 years for graph pattern mining, geospatial analysis, and natural language that are all these domain-specific libraries and make it easier to solve a problem in that specific field. So that's, I think, a trend that we'll see more of this year, more domain-specific libraries. Okay. The next thing I want to talk about is who is doing all this work with data and AI, which is the data scientists and what's happening with those. So in here, there's basically some good news and bad news, at least from the perspective of organizations looking to hire data scientists. So the good news is that there's a large boom of people going into data science and computer science. Actually, this has been happening over the past 10 years, and it's actually a really significant increase. So at most U.S. colleges, computer science and data science are some of the top majors, and the number of students who enroll in them has increased by a factor of 3 since 2008, and it's actually higher now, nearly twice as high as it was at the peak of the dot-com boom. This graph at the bottom here is from the Computing Research Association, and it basically shows average CS majors per unit, where a unit is a computer science department somewhere in the U.S. So you can see it's grown significantly. It's actually not stopping either. There are still a lot of extra new students each year. Many schools have also started offering data science degrees specifically that combine computing with more statistics, which is great for people wanting to work in this field. And just as one data point, at Stanford today, 90% of undergrads take the Introduction to CS course. So even someone who's going to major in literature or in biology or something like that takes at least the introductory course, which is really preparing a lot of people to understand these concepts and work with them. So there's going to be a growing workforce who can work on big data and AI. At the same time, though, kind of the bad news is that even despite this boom in new graduates and, of course, other people switching fields, there's still a lot of demand, and so it's unlikely to satisfy the whole demand right away. There are still many data science openings. They're hard to fill. Salaries are rising, so it's a great time to actually work in this field. So what do you do as an organization in this climate? Our bet at Databricks, at least, is to make the existing data scientists more productive by automating infrastructure. And the good news here is that there's a lot that data scientists do today that it's kind of just busy work or grunt work for them, and that they would love to eliminate, both so they can focus on more exciting problems and also so that their organization can get more projects done. So there's still a lot of work that can be done to improve efficiency here. I'll just talk about, 3 different things that take the most time. So the first thing is when you talk to most data scientists, they say, they spend 80% of their time in data preparation. And this goes back to what I was saying before with it's the data stupid. If you don't have quality data or if you don't have the right sources of data, no matter how good you are at building statistical models, you just won't have the information that you need to actually make reasonable predictions. So how do you solve this? Well, you want to enable collaboration between people. If someone did the work of finding and chasing down and cleaning a specific data set, you want others to be able to build on that. You want to enable visualization and debugging and quality assurance of the data. And you want to enable one-click deployment of production pipelines that will repeatedly load and clean up new data sets so that you can be working with fresh data. And these are exactly the kind of things that we've built up around Apache Spark to let people work with that. The second thing that takes a lot of time and is challenging is experimentation and model tuning. So as you try different approaches to a problem, how do you track, which ones really worked and reproduce them later and so on? And for this, you want an environment that can track versions of the data and the result and code. And what we've seen, what's worked really well for us is this concept of notebooks that are version controlled, stored in Git, including the result and the code. And you can get really far sharing these throughout a team, going back in time and seeing what affected a particular result. And then the final thing that can take time and that can slow things down is passing updates to production engineers. So in many organizations, there's a separate engineering team that rewrites each model that someone builds for production. And you can imagine that that can reduce agility. If you change something in your model, it may take months for someone to implement it and validate it in the production system. So we're trying as much as possible to enable the same people to deploy and update these jobs, or to have a really clean interface between the production engineer and the definition of the model. This is in large part actually due to the design of Apache Spark, which makes it possible to use, both interactively for model building and in a production job that's actually highly efficient. So these are just some of the things that take time. I don't think I've met any data scientist who says that they're only working on really exciting problems every day and that all the data they need is available right away. So I think we'll see a lot more innovation in these areas in 2018 to make folks more productive, let them focus on their specific business problems. Okay. And then in the last 2 sections, I'm just going to talk a little bit about the software that we use for machine learning and big data. And I'm going to start with deep learning software, which is probably the newest kind of machine learning framework that people are really starting to look at in the past couple of years. So deep learning, of course, is a technique for running machine learning on unstructured data, often with a high dimensionality. So things like images and text and audio. And there are now a ton of software frameworks for working with it. So it's really a lot of innovation and people trying different approaches here. At the same time, though, the question is, how will this field move forward, or what are the top issues that people will deal with? So if you look at all these frameworks in terms of fundamental differences, there actually aren't that many differences between them. The top three I could find are the programming model. So there's something called lazy evaluation, where you specify whole computation in multiple steps, and then the engine can optimize it, versus eager, where you tell it exactly which steps to do in which order. There's the programming language. This is probably the biggest difference that's hard to bridge between the frameworks. And there's built-in features such as debugging and model serving. So because there aren't that many high-level differences between these frameworks, there's been a lot of work to help them converge. And I think this is something that will really happen over the next couple of years, is that we'll converge to a small number of these with pretty standard sort of functionality. Already, frameworks like MXNet and TensorFlow, for example, have added support for both the lazy and eager programming models. And there are also efforts like Onyx, which is a standardized model format that allows you to export and exchange a deep learning model between frameworks or push it into a serving system. This is a project from Microsoft and Facebook and a few other organizations. And so I think this is one thing that will happen. The other thing that will happen, I think, is that developers will focus on higher level use cases of the deep learning workflow. So today, if you look at all the frameworks out there, they're mostly targeting model developers, which are most of the time they're actually AI researchers, say at a university or something like that. If you look at all the frameworks, they tell you how easy it is to set up different types of layers, different types of convolutions, fully connected layers, and so on, which is great if you're defining a new model architecture and you need to decide how to put them together. But when you're actually trying to apply a model to a business problem, it's usually not the main thing you do. Usually you actually try to find and run an existing model that someone's published, where they figured out, you need this many type of layers to deal with image data, and you need to do this trick before to transform the image, and so on. And they just want to apply it on their data and make sure they're getting the best possible results. Often they'll try many different models and many parameters for each one. So there's a lot of work now on making these easier for end users, making this workflow easier. And this is one thing we're working as well to make it easy to do this in Apache Spark. So we published this open source library called Deep Learning Pipelines that's about making the end-to-end experimental workflow using existing models easier. So with deep learning pipelines, you can connect standard sort of state-of-the-art models from TensorFlow and Keras into Spark's ML Pipelines API, which makes it very easy to do experimentation with different parameters and to evaluate results. And you can use existing tools for data preparation, model tuning, and evaluation, including, you can use any Java or Python library for image manipulation in parallel using Spark. That's just kind of bread and butter of what Spark does. And so it's just a couple of lines of code to do a lot of the common use cases, which is, hey, let's take, the top two or, the top like 2 or 3 models for a specific task, try them on our data, try tuning them, and so on. Just as one example of what this can look like, I'll talk about a demo we gave actually, which is for image similarity search. And this is a pretty general thing you might do in many domains. For example, in the medical domain, you might have images of X-rays or something like that, and you want to find similar ones from other patients. So it's the basis of a lot of additional applications you could build. In this example, I'll show it using e-commerce. So let's say we have images of products such as shoes, and we want to find ones that look visually similar. So in all these use cases, you've got some domain-specific data. Unless you have lots of images of shoes, you're not going to be able to build a good search system or anything like that for shoes because you just don't have the data. And then after that, you often use an existing model architecture or even an existing pre-trained model with all the weights from somewhere else. So in this particular case, one of the best ways to do image similarity is called transfer learning, where you take a model trained on a large public data set that has just learned general features of images, and then you figure out which of those are most relevant for your specific data. So in this case, you can take a model that's been trained on millions of web images and designed by some kind of AI researcher to have the right layers in the right order, and you can apply it on your data. And these models produce basically a featureization of the images. They map the images into this something called the feature space, where images that are visually similar in terms of texture or other high-level features are close together. So you get, images clustered by similarity. And this is really, it's a common workflow, but it can be pretty time consuming to just write on your own because you don't want to have to build each model from scratch and stuff. So when we tried doing this in standalone deep learning frameworks, it could be as much as 100 lines of code. And then these frameworks are usually single node only, so it could take many hours to train, on a realistic image data set. And if you want to parallelize them, you can do it by hand. With Spark's deep learning pipelines, you can actually do this whole thing in about 6 lines of code and run it on a cluster. And on a cluster of a few dozen nodes, you can train this in 10 minutes. So the key thing we have there is this pipeline component called a deep image featureizer, where you can just put in the name of like a well-known model and apply it and hook it up with other components of Spark's machine learning library in a pipeline. So for example, in this little code snippet, we're hooking up with approximate nearest neighbors. And just by taking this existing model and applying it to domain-specific data, you get really excellent results. So these are some of the pairs of similar products that were returned by this. You can see, it actually catches on specific visual features of these, not just on color or something like that, which is great for what people, want to do when they do search. This is actually a very general technique, and it's often the first technique that someone uses when applying deep learning in a new domain. It's called transfer learning. So if you look at all the state-of-the-art results that were published using deep learning for medical images or cancer diagnosis or even a lot of natural language processing, this is the technique they're using. And in fact, this is also one of the best ways to use deep learning on small data sets because you don't have enough data to actually train a model from scratch. You have to bring in information from somewhere else about what images in general or text in general looks like. So it's a very powerful technique, and it's the kind of thing that, because everyone does it, we want to make it really easy to do this in a few lines of code. So that's kind of the direction that we think deep learning frameworks will go in, find these end-to-end use cases and make them easier. All right. And then the final bit I'm going to talk about is new data architectures or systems for actually managing data. So as I said at the beginning, data is the key component of AI, and we still need better ways to manage it. And even though we've had software to manage, large data sets and do analytics for over 50 years, I think nobody thinks it's simple. Every organization has a lot of trouble with it. It's almost as difficult as it was at the beginning of the industry, which is kind of shocking given how much easier other types of computing have gone. So my prediction here, and based on what we're seeing in the market, is that the cloud will enable new and simpler data architectures than we've had in the past, which will let organizations focus on actually using the data. And there are 3 reasons why the cloud is exciting for this. There's its high global availability. High availability suddenly becomes super easy, whereas it used to be a big operational burden in the past. There's elastic scaling and automatic management. So just as a couple of examples from today's public clouds, there are a number of really interesting products that only kind of make sense in the cloud. It would be very difficult to have a product with the same sort of experience on-premise. So first, even if you're just looking at data ingest, there are these products like Azure Blob Store or Kinesis Firehose or S3 that let you load data into these storage systems via a REST API. And these are highly available. They're geo-replicated. It's running in every Microsoft and Amazon data center, and you can pretty much always reliably upload a blob of data into your system. And in fact, these particular products are actually often free because data ingest into a public cloud is usually free in terms of networking cost. So already these simple, like almost free products can replace much of a traditional streaming ingest system. You don't need to figure out how to distribute this across a bunch of data centers and run it 24/7 and store the data reliably. You can just make a little API call and your data is uploaded and saved. And that's kind of an amazing step that only makes sense because someone else is handling the global availability. Likewise, products such as S3 Select are really changing the game in terms of what cloud storage can do. So S3 Select is a product where you can, when you read data from Amazon S3, you can specify a filter, and it will actually run a computation close to the data to filter it down, and then send you only the stuff that matches. So suddenly, if you have, a petabyte-sized data set and you want to pull out just a few % of it, you can get basically all the machines that are serving that in S3 to work for you and just get back the amount you want and get this instant scaling for, a few seconds to scan through the whole data set. It's, again, something that wouldn't make sense in a small on-premise data center where you don't have those thousands of machines to do this scan. So this is an area where we've been working on quite heavily at Databricks as well. And we've also announced a product that we think is exciting here, which is called Databricks Delta. It's a unified data management system for analytics that basically combines the best of data lakes, data warehouses, and streaming. And this is really tackling a lot of what we see as the ingest and production data pipeline problems from a lot of customers. Every single one of our customers is doing the kind of tasks that Delta simplifies. So I'll just give a quick overview of why and how it works. So in traditional data architectures, people have been building enterprise data architectures for decades, and you usually have 3 different types of components. The first component, and sort of the oldest, is a data warehouse. This is a SQL database. It can have very fast queries because it indexes the data, and it's also highly reliable. It supports transactions, and it's easy to have many people using it concurrently and update the data and keep it consistent. But the downside is that data warehouses are very expensive per byte of data, and also they often have limitations on scale. Second component that became popular in the past decade is data lakes, so something like Hadoop file system or S3 or Azure Blob Store. So these are things that no longer index the data or impose a structure on it. They're just low cost but massive scale. And so you can just put data in there. It's many times cheaper than a data warehouse, and you can hold on to your data and work with it there. And finally, we can have streaming message buses like Kinesis or Apache Kafka. The main benefit of those is low latency. Neither the data lake nor the data warehouse are optimized for that. Now, in practice, these systems have different characteristics in terms of performance and cost. So everyone uses a mix of them. And, it might seem that you're kind of getting the best of all 3 worlds. But in reality, you actually just end up having to do a lot of development just to keep them in sync and move data between them. So if you're going to use all 3 of these systems, you need these complex and slow extract, transform, and load, or ETL processes that are going to move data, from the streaming message bus into the data lake. Maybe you'll process it in the data lake, move some of it into the data warehouse for fast queries. You'll move some back when you no longer want to query that data, and so on. And this process is not just complex and expensive to build; it also slows you down. So it can take hours, for data from the message bus to arrive in the data warehouse. In addition, every application may need to talk to all 3 of these. If you want to combine both the freshest data and historical data, for example, you need to talk to all these systems. And so everyone who works with data in the organization sees the complexity. So in Databricks Delta, we're building a unified data management system that actually provides the best of these worlds using the characteristics of the cloud. So Delta has the scale of a data lake. It's based on cloud data stores like S3, but it adds the reliability and performance of a data warehouse and the low latency of streaming. So you suddenly don't have to move data around. You can just keep it in this one place and get all these properties. And here's how it does that. So basically, Delta uses S3 or Azure Blob Store under the hood for low-cost storage. It means you get the same availability as S3 and the same cost efficiency in terms of dollars per byte stored, which is one of the best you can have for highly available data. On top of S3, though, we add a layer for transactions and indexing that adds the reliability and performance features that that people love about a data warehouse. So you can ingest data at low latency, and then we index and compact it over time. And these indexes make a big difference in performance. Even compared to running Apache Spark on an optimized format like Parquet, you can get a 10 or 100x difference by doing this and really go back and search historical data very quickly. And then internally, we use an open file format, which is Parquet, and it's available as a Spark data source. So you can connect to it the same way you connect Spark to anything else, and you can use it for streaming, batch, and interactive or SQL applications. So if you know how to use Spark already, it's very easy to use this. Just an example of how this works, one company using this is a Fortune 100 company doing information security pipelines. And before Delta, they had a system with the traditional architecture. They had a data lake, and then they had complex ETL processes that built up different warehouses for different applications. And this, this approach had a bunch of limitations. So the data warehouses were limited in scale. They could only store about 2 weeks of data, and it was very expensive to scale them out further. So if you ever have a security incident where you need to look back in time more than 2 weeks, you have to go all the way to the data lake and do some really slow computations. And in addition, the data warehouses only support SQL, so you can't do predictions and AI. So this architecture, caused basically it limited agility. It limited the scale of historical data it could keep, and it was also complex to build. It took 6 months and 20 people to build this initial architecture. Same company started working with Databricks Delta and trying to build the next generation version of this architecture in the cloud. And using Delta, they were able to just use the same storage system for all of the types of data, both the historical and the processed data that they want to serve. And then on top of that, using Spark, they can do simple SQL as well as machine learning and streaming. So the new system gave you an AI-capable data warehouse at the scale and cost efficiency of a data lake. You can now do interactive analysis on 2 years of data, not just 2 weeks. And it just took it only took 2 weeks to build the basic system with a 5-person team. So much faster to set up together as well. If you want to find out more about Delta, the official website has both other technical resources, including a webinar and documentation, so you can read about it there. Okay, so that's essentially what I wanted to talk about. I think 2018 will see a lot of successful AI use cases, but only in domains that are prepared to deal with it. And the single biggest factor that determines that is whether the domain has high quality data, and organizations have built high quality data pipelines to make them successful. So this is what I think the whole industry will center around. And if you want to find out more information from us, you can follow us at Databricks.com. We have quite a number of upcoming webinars and events as well, conferences, where you can learn about some of these use cases. Thanks.
Well, Matei, thank you for that excellent presentation. And we'll get started with today's Q&A session. And I want to thank the audience for their participation. We've had a lot of questions that have come in, and we'll do our best to get through all of them in the time remaining. So during this Q&A session, I'll leave up this screen with contact information for Matei in case you'd like to get a hold of him following today's webinar. So let's get started. Matei, a lot of companies are just starting to struggle with the idea of developing an AI strategy. Do you have some tips from what you've seen for organizations that are just getting started with AI?
Yeah, good question. Yeah, I think there are a couple of things to do. So one thing is, as I said, just understanding what data sources you have access to and making sure that you're at least capturing some of that for use in the future. And then the second thing I'd really suggest is finding a few examples of other successful use cases and just starting with, say, one or two things and trying to do those. So maybe it's not the most, kind of the most amazing or complete use case, but you just want to try to build one as just to gain experience with this. And often by looking around at similar companies or similar problems in another domain, you can see something that someone has done, and you know that it's doable basically, and you can work to see whether you can do that with your data.
Well, those are good tips. Thanks very much. Now, the audience obviously really paid attention when you were talking about data quality. And there are questions that come at this from two angles. First of all, kind of what are the correct measures for determining data quality? That's kind of the master data management question. But also, are you thinking about or working on, or have you heard anything about tools or techniques to detect unexpected biases in data sets like you described with the iris and the MRI problems?
Yeah, it's a great question. Yeah, so there are definitely a number of techniques and tools you can use. At the same time, though, it's difficult if all you have, if the initial data set you have all contains one specific bias, and then later in the future some new data will start to arrive. It's very hard to know about that in advance. So I think in the end, every production application will have some kind of monitoring in production, and a lot of people have just alerts when just the distribution of basic features in the data begins to diverge from the distribution you had in the training set, because they say, look, there's something different in this distribution, and it means the rest of your model may not work. So you need some kind of production monitoring. While you're working with training data, there are a lot of tools to find outliers, for example, that let you focus in on subsets of the data that maybe you have very little information about or that are very different from the rest. And that's what we often see people doing is, even as simple as sorting the data by a specific column and seeing what are the extreme values and pruning them out. Visualizations are also extremely helpful here. But the more general set of tools would be outlier detection and basically anything to determine the difference between two statistical distributions.
Makes perfect sense. Thank you for that insight. Now that AI is so much in the news, there's an awful lot of talk about interpretability and the inability for most AI applications to be clearly interpreted. Would you just comment on where you think we're going with interpretability with these advanced deep learning techniques?
Yeah, that's an awesome question. There's a lot to be said there. And actually, I think this is one of the most interesting things to look at from a regulatory perspective as well. So, for example, in Europe, there are these laws about basically the right to an explanation. So if your bank doesn't give you a mortgage at a specific rate or something, you should be able to ask them, hey, can you show me what algorithm caused you not to give me that, and they should give you an interpretation. And it's actually very interesting to think about because in some sense, maybe this is what we should require everywhere. Of course, a lot of AI practitioners will say, no, we think our models will work well, and we should just use the best model that produces, the best result for the business or whatever. So one interesting thing here is that in some sense, models with very interpretable rules like decision trees can actually be pretty good in many cases. So it is possible to get good results with interpretable models in a lot of cases. For deep learning, it's difficult. I think the best thing you can do is essentially show a human similar examples in the data set so that they can figure out what about them was similar and they can make a decision. So I think that's kind of the best case that we can see. But I think it's fundamentally challenging because there are just so many different features you can have in your model. It's hard to visualize and understand each of them. But yeah, I think it's a fascinating field, and there's going to be some, like as a society, we have to decide on the regulations you want here in order to make this work well.
Well, Matei, thank you. Those were some great answers to some very good questions. Now, for those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Matei and the Databricks team so they can follow up with you after today's webinar. I have just a few quick announcements. If you'd please mark your calendars for February 27th. That's our next DSC webinar, which will be sponsored by Trifacta. And also please remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, that brings today's webinar to a close. I'd like to thank our audience for their attendance and the thoughtful questions, and a real special thanks again to Databricks for their sponsorship, and our speaker today, Matei Zaharia, for his insight into today's topics. This is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on February 27th. Have a great day.